today by Pietro and Laurent from my group. And none of them could be here today, so I take on the glory of use. So this is about recognition of object categories, which is something that my research group has been interested in for a while. The best estimate we have of how many categories we can recognize comes from our Earth Biedermann here. And it's depending on how you count categories, whether you look for entry level or whether you look for all categories, you get different numbers. But in order of magnitude would be 10 to the 4th. So by the age we have 6, we know about 10 to the 4th object categories. And if you count how many days that are in the life of a child of 2,000 days, it's many categories per day. It looks like we must learn. And if you look at what the machine vision literature does, where are we at the moment? So there are two observations we can make. One is very few categories are demonstrated by systems, so people can't use their systems for some categories and they don't do too well for others. It's very difficult to do experiments anyway. But what I would like to talk about today is a different issue, which is how many training examples do we need to learn a category? So how much information do we need to get? How many parameters do you need to train? So you start thinking, well, if I have to have a model which by tuning parameters can represent ice cream cones, sailing boats, skateboards, my shoes, your grandmother, and so on. So the same model by tuning parameters represents all of these things. Then I probably need quite a few hundred parameters. And so a statistician would tell you, well, if you have a few hundred parameters and maybe 1,000 parameters, then you need a few thousand training examples. So a rule of the thumb is 5 times the number of parameters, for example, for training and test curves to converge. So those numbers you find in the machine vision community are not so crazy. We do need lots of training examples. And so is our intuition that for us humans it takes fewer examples to learn something, is it completely mistaken, deluding ourselves maybe that we're so good, but if a statistician tells me that there are hard numbers, I must either believe him or I must get some better theory about it. And this is an example generated by my student Silvio Savarese. Here I demonstrated to you that you can learn categories from one example. So you've learned it. And now I test you. Can you find it? Okay. So it's correlated with IQ, by the way. So it's very. And so this would be one example. And there is another one. So where are we? So here we have a demonstration that we can learn a category from just one example, but the statisticians tell us you need many thousands. So how do we make sense of these large discrepancies? And so my intuition is we may need lots of examples at the beginning of our life when we start off tabula rasa and we don't know anything about the world. But when we learn a new category at our age, we can benefit from an enormous amount of experience. We have learned categories before, and maybe there is something that we can transport, some generic piece of information we can transport from these categories to the new ones. And so the idea would be that instead of having to learn a new category from, or being able to learn a category from an example, which is ridiculous, well, but you have learned other stuff before, and so in this case, each one of us felt that maybe we identified some human parts and some vase parts, and we use those two categories to help in making this new category. And so the theme of the talk is to take a Bayesian point of view. So we have a hypothesis that we can incorporate prior information, and we're going to explore it in a Bayesian setting. So we'll use exactly. And not what they're exploring today, but yes. So we are going to incorporate what we know about different categories in a prior, and then we're going to use some Bayesian technique to do it. So the question is what to do. What to do about it. And so the intuition here is that not only, we should let me go back one slide. So here, somehow we make a somewhat literal assumption, which is that we extract parts of previously learned examples, and we can concatenate or combine these parts in order to compose a new one. What I'm exploring today is something even more generic, namely that from previously learned categories I learned very somewhat vague but useful pieces of knowledge, such as it is more likely that something like this is a feature than something like this is a feature, or that the shape of the object is more likely to be like this than fractal like that. So we're going to try to use prior knowledge to learn this kind of information. So here is the idea. In order to do detection, we want to know what is the probability that a given object is in our picture, a given object belonging to a certain category, given the test image that we have at hand and all of our training knowledge. And we're going to contrast that with what is the likelihood that there is no object, no motorcycle, it's just other stuff. And the idea then is to use Bayes' rule to expand this and to predict what is the probability, so to use the probability of the test image given a model of objects and training images, and use a parameterized model in which we represent the probability of the test image in parametric form, and we have previously estimated what are the parameters that represent the object category. So the whole action is, where do we get a model that represents the object category from just one example? And in previous work we did, and other people did, this estimate of what parameters would be is derived in a maximum likelihood setting, and therefore you need an enormous number of training examples, as everyone would expect. You need lots of training examples to estimate the parameters of a model that encodes the appearance of a given category. So lots of ice cream cones to know what ice cream cones look like. And today we're going to take a Bayesian setting, so we have to make that a little bit softer. And so you want to represent that probability density and not as a delta function, but as a distribution over all possible parameters. And the model we use for representing objects is along the lines of what's done before in my group. You have parts of objects that have a certain characteristic appearance, and so here we have two parts that are different in general terms, but if you look through peepholes, you find that there are lots of similarities, and you take advantage of that for representing objects. And so you represent the appearance of parts, and you represent the mutual position of parts, and all of this in a probabilistic setting. So the shape of this constellation is a probabilistic function, the appearance is a probabilistic function, and so you have parameters to represent what things look like. So this is the specific of the model that we use. And so the idea is that in the maximum likelihood setting, you have a single parameter that accounts for everything that you know about a certain model category. And instead, you have to soften that and represent, instead of a point, a probability distribution. And so think about it as a probability distribution of density over in a parameter space, and each point in that parameter space defines a probability distribution which encodes for the appearance of a category of objects. So there are a few levels of indirection. So there are object categories which are represented by a probability density function, and then you have a probability density function and parameters of that density. That is what we're going to use today. And so the idea is how do you estimate it? And this is work done in part by Joe Easton and others. And I will only give you a little sketch. It looks very much like your typical EM algorithm, in which you start off with a broad view of what the probability density looks like, and given your training example or examples, you can iterate, and this becomes that you bias it towards the final solution. So in our case, we'll only have one data point, or 5 or 10 or 16, if I remember well, and we have to make this. We have to get by results. So you start off with a density which is estimated from other categories from your prior knowledge, and you define it through this procedure. Okay, so just experiments. So this is the first experiment. We have 4 data sets. You recognize this person, motorcycles, cats, airplanes, and so on. And these are examples. As you will notice, there is a lot of clutter in these images. You don't normalize the images. The system is able to learn by itself which ones are the significant features. And so the typical experiment we do consists in learning each one of 3 out of 4 categories from lots of examples, maybe 200, using maximum likelihood setting. Each one of these gives us a point in data space, in parameter space. And then you can fit a Gaussian, to speak, there are other densities involved, to those data in order to generate your prior, and then you're going to use that prior to learn the new categories. And this is it, yeah. And so these are results of experiments. This is faces, and so in this case we use cats, motorcycles, and airplanes to generate the prior, and then one face to learn faces. And then we use the model that we obtained in order to discriminate between images containing faces and images not containing faces. So that's the experiment. And so 50% correct is chance. And we see that with 0 training examples, the prior does not allow us to do any better than chance. With 1 training example, there is already a considerable improvement. And now if you average, so there are error bars here, the improvement continues to grow with more and more training examples. This is for motorcycles, and so in this case the prior was derived from faces, airplanes, and cats. And up here we have a maximum likelihood, which doesn't do very well at all. It's always a chance. This is airplanes, again, learned from 1, 2, 3, 4, and 6 training examples. This is cats. This is more or less the same pattern in which you see a big benefit between benefit coming from the prior, but the prior is not encoding specific information, it's only encoding generic information. And here are more recent experiments done in the last couple of months on more categories of objects. So these are derived from Google by typing words, and you get lots of images from Google. So these are, again, rhinoceros, beaver, cougar, and so on. So each one of these images symbolizes a category, and it's in fact extracted from the data set. So there are 101 categories. So you can guess what, and there is no specific rhyme or reason, it's what we could obtain easily from Google. So in this case, I forgot what category it is, I think it's tempo or something like that. You see that are somewhat noisy. Okay, so here is how we plot the data. This is what happens with, so ignore the red circles. There's an incremental method. I'm talking only about the batch method. This is what the prior allows you to do. And you see that it's slightly better than chance if you take the mode of this cloud of points. So here there are 101 points. And the prior gives you a few points above chance. And with 1 training example, you're already around 65 or 70% correct. With 3 training examples, you go up to maybe 75, something like that. This is maximum likelihood, which of course is down at chance. And it's only around 15 training examples that maximum likelihood catches up. So here is 6 and then 15. At this point, the model is down at maybe around 85% correct or so, which is certainly not perfect, but way above the signal translation. Okay, so what I hope I've convinced you about is, first of all, there is a big problem in learning categories. We want to learn categories from few examples. It is too expensive to wait long enough to collect all the examples that your statistician friend would want you to collect. Second thing is, there is hope. If you have learned already a few categories, as few as 3, as in our experiments, you may treasure that information, even if those categories are completely unrelated to the category that you're going to learn next. There is some information there that you should be able to extract and make use of. Third, there is a practical way to act upon this intuition. A Bayesian framework seems to be able to deliver at least some of the goods, so there is way forward. Fourth, it seems to be robust over a large number of categories. At 100 categories, we're far from the 10,000 or 30,000 Earth would want us to work with, but at the same time, we don't see any significant pathology in those categories we use. So it seems to be reasonable. It is clear that there is an enormous amount of work to be done. How do we build priors in a proper way? Suppose we had lots of categories that learned well, how would we combine them into a prior? More work needs to be done on how to taxonomize information. So this morning, Josh was saying the dream of my career is, and so this would be the dream of my career for today at least. It's that we would be able to get lots of images, not sort them out by categories, but really feed them into the machine as they come from Google, and end up with a taxonomy which is built automatically out of all of these images. So a way of ordering categories of objects by their visual similarity, which may not relate to what their function is in the world, but it will certainly be highly correlated and therefore useful. Thank you very much.